So for this week, we are looking at confidence intervals in Chapter 9, basically looking at estimates of population parameters. Now we have point estimates, where a point estimate is just taking a sample and calculating the statistic from that sample, and then using that sample statistic as an estimate for that population, the corresponding population parameter. We might take a sample and find the mean of that sample, and then use that sample mean as an estimate for a population mean. Or we could do the same with a sample proportion to estimate a population proportion. So suppose we want to estimate the proportion of blue candies in a very large bowl. How might we go about estimating this proportion? Well, if we don't want to take all of them out and count them, there's got to be an easier way. We could take a sample of those candies and compute the proportion of blue candies in that sample. Now again, we have to be careful. That is a randomly selected sample so that hopefully we get a representative sample. We would have a sample proportion or a statistic for that sample, and that would be a single value estimate, or what's called a point estimate. So a point estimate is a single number, a statistic from a sample, based on that sample data that is used as an estimate of a population characteristic or population parameter. So let's say that this arrow here refers to the single, well, the point refers to a single value on the number line. Let's say the arrow is our population parameter, and that point is our sample statistic. Usually it'll be relative. If we took a good sample, a representative sample, that should be relatively close to our population characteristic. Not always will that be equal to the population characteristic because, laid over itself here. Anyway, it won't always be equal to the population characteristic because there's variation in our samples. Remember, there's variation in that sampling distribution. So different samples will produce different sample statistics. So in other words, different estimates. Well, we don't like having different estimates because how do we know which one to use? So in the paper, the U.S. College Students' Internet Use, Race, Gender, and Digital Devices, Journal of Computer-Mediated Communication in 2009, this article reports the results of 7,421 students at 40 different colleges and universities. The sample was selected in such a way so that we can be relatively assured it's a representative sample of the population of college students. The authors wanted to estimate the proportion of college students who spend more than 3 hours a day on the internet. 2,998 out of that 7,421 students reported that they did use the internet more than 3 hours a day. We calculate that proportion. Now this is p hat because it is from a sample, not from the whole population. 2,998 divided by 7,421 gives us a point estimate of 0.404. So that is our point estimate for the population parameter. So it's an estimate for the population parameter, but we use the sample to create it. So next, using that same article, we investigate the reading habits of college students. The following observations represent the number of hours spent on academic reading in 1 week by 20 different college students. This dot plot suggests this data is approximately symmetrical. So one of the things we want to do in order to use some of these statistical processes is we need to assure ourselves that the data is approximately normally distributed. And so by doing this dot plot, that assures us that it's relatively symmetrical or approximately normally distributed. If the point estimate of mu, the population mean, for the mean of the academic reading time per week for all college students is desired, an obvious choice of that statistic for estimating mu would be the sample mean, x bar. That bar got a little off center, it should be right over the x like that. However, there are other possibilities. A trimmed mean or a sample median could also be used. A trimmed mean, remember, you just remove any outliers and then calculate the mean. Or the sample median, if the data is truly normally distributed, the mean and median should be the same number. So continuing with this set of data, we'll calculate the sample mean. We add those up, we get a total of 287.2. Divide by 20 because there were 20 numbers in that list. We get a sample mean of 14.36. The median of that sample is 13.75. We put them in order smallest to largest, and we find the two middle numbers, since there's an even number, and the median is between those. The 10% trimmed mean, which is where we remove 10% of the data on each end. So that means we take away the two smallest and the two largest. 10% of 20 would be 2. We get a mean of 14.39, very close to the sample mean, the full sample mean, which means that those really aren't outliers. They're balancing numbers. It's not skewed. The data is not skewed in any direction here. So which of these estimates would we use? Well, we want to choose the statistic that is the most unbiased or the most accurate. In other words, the one that's going to most closely represent the population parameter. So a statistic whose mean value is equal to the value of the population characteristic, being the estimate, is said to be an unbiased statistic or an unbiased estimate. Now looking at these diagrams here, if the true value is represented on the axis down here, this one is the most unbiased because the center of that bell curve is at the true value of the population parameter. Now remember, all those samples we take, they're going to give us values that are going to follow that bell curve. We want the one that's in the middle. This one's also unbiased because its center is also over that true population mean or true population value. It's just got less variation. It's got less variation most likely because we took a larger sample. This one is biased, however, because the center of that bell curve is not at the true population value. So we want to choose an unbiased estimate. We also want to choose a statistic with the smallest standard deviation. So the one that's going to vary less away from that true population value. So both of these are unbiased, but this one has a larger standard deviation. That curve is more spread out. This one has less standard deviation. It's a tighter curve, a narrower curve. So because of that, we would rather use the one with a smaller standard deviation. Unfortunately, most of the time we don't know what that standard deviation is. So suppose we want an estimate of the population of blue candies in that very large bowl. We could take a sample of those candies and compute the proportion for the blue candies in our sample. So how much confidence do you have in this point estimate? Would you have more confidence if your estimate were an interval? So we know that that point estimate that could vary based on that bell curve of our sampling distribution. We would be more confident that we have an estimate of our true population parameter if we were to say, give a small interval and say, well, we think that it's within this interval rather than saying we think it's at this number, this single number. That's the idea of confidence intervals. The level of confidence measures, I don't want to say the likelihood, but it measures the percent of the time that that size of a confidence interval should contain the true population parameter. So the primary goal of the confidence interval is to estimate that unknown population characteristic. So we construct it such that with a chosen degree of confidence, that's 95% or 90% level of confidence, the actual value of the characteristic will be between the two endpoints of that interval. So rate your confidence. How confident are you that you can do certain things? From 0 to 100%, guess my age to within 10 years. Depending on the situation, most people would be relatively confident they can guess another person's age to within 10 years. To within 5 years, well, that's going to be a little bit trickier. So within 1 year, that's definitely even trickier. So to get within 1 year, we need a much higher level of confidence. To be within 10 years, we're pretty confident we can do that. Well, I should be here. To get within 10 years, we're very confident we can do that. So that we're pretty sure that we can hit that mark. So that's a high level of confidence. To be within 1 year, we would have to be kind of lucky. So it's a much lower level of confidence that we can manage to get within 1 year. So what happened to your level of confidence as the interval became smaller? We're less confident with the smaller intervals. So this is basically what happens with confidence intervals. We're setting a confidence level, and the smaller our interval is, the lower our level of confidence is that that interval will contain the true population characteristic. So let's look at our method to construct confidence intervals. This method was used to generate an interval estimate over and over again. So we would repeat this process over and over again. If we said it's a 95% level of confidence, that means 95% of the resulting intervals created using that process would actually contain the true population characteristic. So our confidence in the method is not, the confidence is in the method itself, the way we created the interval, not in the actual interval. So when we say that we're going to a certain level of confidence, to 90% level of confidence, we're saying that this method, 90% of the time, will create an interval that contains the true population characteristic. We're not saying that the interval itself has 90% confidence. We're saying the method used to create that interval will produce the true population characteristic 90% of the time. So the most commonly we use 90, 95, or 99% levels of confidence. So let's recall the general properties for the sampling distribution of p hat. Remember the mean of the p hat, so the mean of all the sample proportions should be equal to the population proportion. Second, the standard deviation of p hat, so the standard deviation of those sample proportions will equal the square root of the population proportion times 1 minus the population proportion divided by n. And as long as it's a large sample, in other words, n times p is greater than 10, and n times 1 minus p is also greater than or equal to 10. The sampling distribution of p hat is approximately normal. So these are the conditions that must be true in order to use the sampling distribution to calculate a large sample confidence interval for p. So let's develop the equation for the large sample. To begin, we'll use a 95% confidence interval, just because our table of standard normal curve gives these pretty easily. Z star is what we're going to refer to as called the critical value of Z. Z star is the critical value. It's a Z-score such that 0.95 of the area of the curve, or 95% of the area of the curve, falls between that negative value of Z star and the positive value of Z star. So on our curve, 95% out of the middle. The other 5% gets split equally to each end, so that'd be 2.5% to each end. So a probability of 0.025. So this here would correspond to an inverse normal of 0.025, because the area to the left of that is 0.025. This here would correspond to an inverse normal of 0.975, because the area to the left of that is the 0.025 plus the 0.95, which is 0.975. Or you could look at the area to the left as 1 minus the area to the right, 1 minus the 0.025, giving us the 0.975. So 95% of the values will be between negative 1.96 and positive 1.96 as the z-scores. So now we just need to then convert those z-scores into actual values for the sampling distribution. So we can generalize this to normal distributions other than the standard normal distribution. So this is for standard normal distributions because those are z-scores. To do that, we adjust using the standard deviations, or for a sampling distribution for the standard error. So here for a sampling distribution for a proportion, Remember, the standard error or the standard deviation of the sample proportions is the square root of p times 1 minus p over n. We'll multiply that times that z-score of 1.96. This is going to give us something called our margin of error. So we calculate that out, and our interval will go from p hat, remember that's our sample proportion, minus that margin of error, ME is what I'll use to abbreviate margin of error, to p hat plus the margin of error. And this will, if we do this 95% of the time that we do this process, that range will contain the true population mean. So if this is the mean of the sampling distribution, that's our P, which remember is equal to the population proportion. This bell curve represents the sampling distribution for those sample proportions. We go 1.96 times that standard error to the left, and we go the same distance to the right. That range should contain the proportion of 95% of all the samples we could take. So now the problem is we don't know what that population proportion is. We're just taking a sample. So we take a single sample, and around that sample we create an interval with that same margin of error, that same distance on each side. So notice this was our sample proportion. We created an interval that far to each side. Notice it contains the population proportion. Take another sample. Notice, again, that sample, if we take the interval to either side of it, contains the population proportion. Here's one, however, we create that interval, we go that distance on each side. It does not contain the true population proportion. Remember, this is a 95% confidence interval, which means 95% of the time, this process will create an interval that contains the true population proportion. This is part of that 5% where it didn't. So we use this method to calculate the confidence interval will not always capture the true population proportion. It'll be 5% of the time, the population proportion will be outside of that interval. When n is large, a 95% confidence, so when the sample size is large, the 95% confidence interval for P is P hat, that's the sample proportion, plus or minus 1.96, that comes from the 95% off the bell curve, times the standard error of the proportions. So here, if we take several samples and we create the confidence interval about the sample proportion of those samples, we see that 95% of them contain the true population proportion. If we made 100 of them, 95 out of the 100 would contain it. We see that there are a few here. There's actually 7 in this illustration that don't contain it, but on average there would be 5 that would be outside. Note that the ones with asterisks do not capture P. So the ones that are in the brownish color are the ones that don't contain the true population proportion. If we were to compute 100 more confidence intervals for P from 100 more different samples, we would get similar results. So let's look at a more general formula for the large sample confidence interval, where P hat is the sample proportion and the sample size is large. N times P hat is greater than 10, and N times 1 minus P hat is also greater than or equal to 10. If the sample is selected without replacement, and the sample size, remember we said, is at most 10% of the population, the general formula for the confidence interval for the population proportion P is P hat plus or minus the critical value. Remember, the critical value, Z critical, comes from our level of confidence, and this is just our standard error of the means, or standard deviation for that sample proportion. So that is our generalized process for doing this. What I have circled there, by the way, is called the margin of error, or sometimes called the bound on the error estimate. So for the 95% confidence interval is based on the fact that for approximately 95% of all random samples, P is bound within an error estimate of little p. So as I said, this is also called the margin of error. That's the more commonly used term for it, is margin of error. So in another article, How Well Are U.S. Colleges Run, describes a survey of 1,031 adult Americans. The survey was carried out by the National Center for Public Policy, and the sample was selected in a way that makes it reasonable to regard the sample as representative of adult Americans. Of those surveyed, 567 indicated that they believe a college education is essential for success. So the point estimate here is the 567 that said yes, divided by the 1,031 total surveyed, giving us a point estimate of 0.55. The 95% confidence interval for this estimate, remember, we're going to use that point estimate and then our margin of error. So first of all, we need to make sure the conditions are met. N times P is, P, remember, is that point estimate, P hat. 10,031 times 0.55 is 567. N times 1 minus P hat, that'd be 1,031 times 0.45, that's 364. Both are bigger than 10, so the sample is large enough. Also, we're assuming that the sample size is much smaller than our population. If we're looking at a population of adult Americans, that's over 300 million people. 1,031 is definitely less than 10% of the population. Next, the sample was randomly selected. Generally, it has to be done in a simple random sample. So our conditions are verified. We can go ahead with the confidence interval. So that's our generalized formula. For 95%, P critical is going to be 1.96. Our point estimate we already found to be 0.55, so we put that in for P and 1 minus P hat, and our sample size is 1,031. So 0.55 minus that margin of error gives us 0.521. 0.55 plus that margin of error gives us 0.579. So we are 95% confident that the true population proportion is in that range. What that's saying is now, since that is all greater than 0.5, we're saying we're 95% confident that more than half have faith in the college education. So our conclusion, we are 95% confident that the population proportion of adult Americans who believe that college education is essential for success is 52.1% to 57.9%. Now, if we want to do a 90% confidence interval, all that's going to change is our critical value. If we did our bell curve, now it's 90% in the middle. So the other 10% gets split to either side, so that'll be 5% on either side. So this would correspond to the inverse normal of 0.05, and this would be 0.95. That gives us 1.645 is our critical value of Z. So we calculate with that, we get this range. Now notice that is a smaller range. Remember, a smaller range is less confident. Lower confidence level gives us a smaller range. 99% confidence level, again, it changes that Z. Our Z critical value is going to be much larger, giving us a much larger range. More confident requires a larger range, larger target. So what do you notice between the relationship between confidence level and the width of the interval? Again, higher confidence level means wider interval. We can also use this to choose a sample size to use. Let's say we want our sample statistics to be within a certain error, a certain margin of error or bound on error for the population. So let's say we want to find the bound on the error estimate for a 95% confidence interval. That bound, or that margin of error, I prefer margin of error better than B for bound. But anyway, is that 1.96 is the critical value of Z times P times 1 minus P over N. So we have to have an estimate for P in order to calculate the required sample size. If you recall from our meat session, if we don't have an estimate for P, then we have to use 0.5. 0.5 is the worst case scenario. Now we solve this for N, so we're going to have to, divide by the 1.96 and square to get rid of the square root, and then multiply by the N and so forth. I'm not going to go through the algebra with you. We come up with the formula that N equals P times 1 minus P times, remember the 1.96 is just Z critical, over our margin of error or bound on the error, and that portion is squared. And that'll give us our minimum sample size to achieve that small of a bound on error, that small of a margin of error. We always round this calculation up because that would be the smallest sample size. So rounding down would be going below the minimum. So sometimes it is feasible to perform a preliminary study so that we can estimate the value of P and put it in here. Remember, if we don't have that estimate, we have to use 0.5, which is going to give us a larger sample, significantly larger sample, than if we have a reasonable estimate of P. In other cases, prior knowledge may give us a reasonable estimate of P. But if there is no prior knowledge and it's not feasible to do a preliminary study, then we use that conservative estimate of 0.5, which is going to give us a much larger sample requirement, which is playing it safe because a bigger sample is going to be big enough, even if we used a different number of P. So for example here, why is 0.5 the most conservative estimate? Well, let's say P was 0.1. It'd be P times 1 minus P would be 0.1 times 0.9 or 0.09. If it were 0.2, we get 0.16. And we can see the different values of P here until we get up to P of 0.5. Well, 0.5 times 1 minus 0.5 is 0.25. If P were to go up to 0.6, well, that's the same as what we had up here. Notice it's going to get smaller again. So the largest possible value of P times 1 minus P comes when 0.5 is equal to P. So in spite of potential safety hazards, some people would like to have an internet connection in their car. Determine the sample size required to estimate the proportion of adult Americans who would like internet connection in their car to within 0.03. So we want our bound on our error to be within 0.03. 95% confidence, well, it's going to be 1.96 will be our Z critical. So that's a bound on our error. 1.96 is our critical value of Z. For P, since we don't have an estimate, we're going to use 0.5. So 0.5 times 1 minus 0.5 is 0.25. 1.96 for our Z critical over 0.03. That was our bound on our error from our problem. We square that portion of it. We get 1067.111. Even though that's closer to 1067, remember 1067.111 is the minimum sample size. If we round down, we're going to go below the minimum. So we always round up on a sample size calculation. So that's going to give us a sample size of 1068. That is the smallest sample that we can take that would give us relatively guaranteed at 95% confidence to be within 0.03 of the population proportion. Now let's look at estimates for the population mean. So we got kind of the same process. We could take a point estimate by taking a single sample. Well, the general formula now, if we want to do an interval for the population mean, is going to be the same. It requires the point estimate of X bar, the sample mean, requires a critical value of z if we know the population standard deviation. That's what we're saying here is when sigma is known. Sigma is that population standard deviation. So it'll be a value of z. And then the standard error, which is just the standard deviation divided by the square root of the sample size. So the sample size needs to be large, bigger than 30. And the population standard deviation needs to be known. And of course, that first requirement has to be a random sample. So these are the properties of the sampling distribution for X bar. So then the confidence interval for the population mean is going to be X bar, our point estimate, plus or minus our critical value times our standard error. That is our margin of error or bound on error again. So the weakness here is it requires us to know the population standard deviation. In reality, it's not common that we actually know that. The confidence interval is appropriate when n is small, if we're looking at a small sample size, as long as it is reasonable to think that the population distribution is normally shaped. So for example, cosmic radiation levels rise with increasing altitude, promoting research to consider how pilots and flight crews might be affected by increased exposure to cosmic radiation. A study reported a mean annual cosmic radiation dose of 219 mREMs for a sample of flight personnel of X-Injing Airlines. Suppose this mean is based on a random sample of 100 flight crew members. Let sigma equal 35. So that is the standard deviation of the population is 35 mREMs. Calculate the interval, calculate and interpret, I should say, a 95% confidence interval for the actual mean annual cosmic radiation exposure for X-Injing flight crew members. So we need to verify the conditions are met. First of all, it is a random sample. The size is greater than 30, and the population standard deviation is known. So our calculation, we have 219 is the sample mean. That's our point estimate. 1.96 is our critical value for Z for 95% confidence. 35 is our population standard deviation divided by the square root of our sample size of 100. That is the standard error of the means or the standard deviation of the sample means. Gives us this interval. So again, we are 95% certain that the true population mean is in that interval. So what would happen if we changed the confidence level to 90% instead of 95%? Well, just like with the proportion, lower confidence is a smaller interval. It'd make the interval narrower. So for confidence intervals, when mu and sigma are known, in other words, the population mean and population standard deviation, or sort of the confidence intervals for the population mean when the standard deviation is unknown, I should say, we are not able to use the same formula. Because if we don't know the population standard deviation, we can't accurately create that z-score or work backwards from that z-score. So because this value of S, we're going to have to use the sample standard deviation in place of the population standard deviation. However, the sample standard deviation is usually larger, more variable than a population standard deviation. To account for that, we have to use a different curve. It can't be the standard normal curve anymore. We use the distribution of t-values. The distribution of t-values looks a lot like the normal curve, only it takes into account how many items are in our sample. It's called degrees of freedom. When the sample size gets above about 100 to 120, the t-curve becomes exactly the standard normal curve. So the properties of the t-distribution, It depends on the degrees of freedom. That's the sample size minus 1. So the t-distribution corresponds to any particular number of degrees of freedom, is bell-shaped, and is centered at 0, just like the standard normal curve is centered at 0. And it's bell-shaped, but what changes slightly is the standard deviation based on the degrees of freedom. Each t-distribution is more spread out than the normal distribution. So it has more variability to it until we get up to those large enough sample sizes where they basically become equivalent. So that's the z-curve. The t-curve you can see is going to be wider. Z-curve's a little bit taller because it's skinnier. Wider means we have to be a little bit lower at the peak because the area under the curve is always totaling 1. So important properties of the t continued. The number of degrees of freedom increases. So as the number of degrees of freedom gets larger, the spread gets less and it becomes closer to the normal curve. So this is the curve for 2 degrees of freedom. For 8 degrees of freedom, you can see it gets narrower. If we keep going, it would get narrower yet. So as the number corresponding to the degrees of freedom increases, the corresponding sequence of t-distributions approaches the standard normal curve. In other words, as the degrees of freedom get sufficiently large, the t-curve becomes basically the normal curve. So for what degrees of freedom would the t-distribution be approximately the same as the standard normal distribution? Every textbook uses a different value here. Like I said, if you get over 100 to 120, it's almost exactly, but some textbooks allow you to go down to even as low as 30 to be a good approximation. So let's look at the general formula for a confidence interval to estimate the population mean when we do not know the population standard deviation. We have to know X bar is from a random sample. The population distribution has to be normally distributed, or, that's an or there, we don't need one of these two. Either we need to know that the population is normally distributed, or we need to know the sample size is larger than 30. And we need to know that the population standard deviation is not known. So in that case, we use the sample standard deviation in place of sigma, or the population standard deviation, and we use a t-value instead of a z-value. So the t-value, remember, has to be based upon our degrees of freedom. So the confidence interval is appropriate for small n. In other words, if n is less than 30, only if we know that the population is approximately normal. So for the articles, chimps aren't charitable, summarizes the results of a research study published in the journal Nature. In this study, chimpanzees learned to use an apparatus that dispersed food when either of 2 ropes was pulled. When one rope was pulled, only the chimp controlling the apparatus received food. When the other rope was pulled, food was dispensed both to the chimp controlling the rope and also to the chimp in the adjoining cage. The accompanying data presented the number of times out of 36 trials that each of 7 chimps chose the option that would provide food to both chimps, in other words, the charitable response. So let's compute the 95% or 99% confidence interval for the mean number of charitable responses for the population of chimps. So first we need to verify that this is met. This is a small sample, so we need to know that this is approximately normal, and that's given in the problem. We also need to know that it was randomly selected, and it is. It says it's random selection of chimps. So its sample is representative, so we know that it was randomly selected, so we know it's a representative sample. It's approximately normal. If you wanted to, you could use the normal quantile plot or probability plot, or you could use a dot plot. There is that normal probability plot. It's close to a straight line, so it's approximately normal. So let's go ahead and calculate. X bar is our point estimate for the mean. That's 21.29. Since we don't have the population standard deviation, we calculate the sample standard deviation of 1.8. Sample size was 7, giving us 6 degrees of freedom. So at that 95% or 99% confidence level, the critical value of t is 3.71. So that's from the 99% confidence level. 21.29 is our point estimate. 1.8 divided by the square root of 7 is our estimate for the standard error of the means. So that is our 99% confidence interval. We could also use this process in reverse to choose a sample size. To choose a sample size, it only really works if we know the population standard deviation. So once again, we took that margin of error or bound on the error formula that we have here, and we're going to solve it for n. Again, I'm going to leave the algebra up to you, but we get that n is equal to that critical value of z times the standard deviation divided by that desired bound on our error, and all of that is squared. So we can use this to find the necessary sample size to be within a certain bound on our error. Again, it requires us to know the population standard deviation, which is very seldom the case, but we might have other estimates of it that we can use. Otherwise, we can do a preliminary study and use the sample standard deviation, or we can make some other educated guess. One is if we have an idea of the range of the data, as long as it's relatively symmetrical and not too skewed, we can just take the range divided by 4 is one method of estimating that population standard deviation. So for example, the financial aid office wishes to estimate the mean cost of textbooks per quarter for students at a particular university. For the estimate to be useful, it should be within $20 of the true population mean. So we want to bound our error to $20, plus or minus $20. How large of a sample should be used to be 95% confident of achieving this level of accuracy? So 95% gives us that Z critical of 1.96. So the financial aid office believes that the amount spent on books varies with the most values being between 150 and 550. There wasn't an estimate given in the problem for the population standard deviation, so we use the range 150 to 550, that's a range of 400. We're going to take that range and divide it by 4 to get an estimate of $100 as the standard deviation for the population. So then we're going to use that in our sample size. Again, the 1.96 is from the 95% confidence, times 100, that's our estimate of the population standard deviation, divided by 20, squared, gives us 96.04. Remember, even though that's close to 96, we always round up because this is a minimum sample size. If we rounded down to 96, that would be too small, no matter how close it is. So we round up to 97 is our minimum sample size. So that is it for confidence intervals. If you have any questions, please let me know. Otherwise, have a great week.